In today's video, we're going to look at how we can determine whether or not triangles are similar. And so we have our definition that will look at this, as well as a couple shortcut methods, kind of like we were when we were proving triangles congruent last unit. So first off, we need to define what similar polygons are, specifically similar triangles. Again, polygon is just a many-sided figure, so triangles are included in that. Anytime we have a similar polygon, they're always going to have the same overall shape. So they'll both be triangles or rectangles or what have you. And they're going to have the same angles. However, they're going to have different side lengths. I actually should have left two spaces but that's okay. So same angles, different sides. But their sides that correspond, they are going to have to be proportional. And technically, the ratio of that corresponding sides, that's what we call our scale factor that we talked about last time. Okay, and if polygons are similar, then they are also proportional, and what we can put in there is perimeter. And so again, we alluded to this last class. Don't forget, perimeter is the length of all the sides added together. So if all we're looking at is our lengths, those are going to have, or they should have, the same scale factor, that same ratio as just comparing like one side to another. Alrighty, so the scale factor, how we can state this with our different diagrams, the order is very important on this. So always pay attention to what order the triangles or the polygons or whatever you're using are stated in. So in this first one, what is the scale factor of ABC to DEF? Well, specifically, it's mentioning ABC triangle, the top triangle, to the bottom triangle, DEF. So if these are similar triangles, then that means our corresponding pieces should match up. And if I look at the marks on my triangle, I'm noticing, for example, I've got like B and C, that the angle marks that touch those, we have the 2 on the top and the 3 on the bottom right, and we have the same thing happening with E and F. So if I compare those two sides, the 10 and the 15, well, to do the scale factor again, we always want to reduce our fractions. So we would reduce out, what's our common factor between 10 and 15? Okay, we could reduce out of 5. So we would take that down to 2 over 3. Or we could also express that as 2 colon 3. But if we change our order, so on the second one, it says, what's the scale factor of triangle DEF to ABC? Well, the second bigger triangle is actually named first. So we would want to flip our ratio over. So we would actually state 3 to 2, or we could state it as the kind of written out ratio 3 colon 2. And so then our third piece, what is the ratio of the perimeter of ABC to DEF? And so just to prove that this is true, again, the perimeter should have the same ratio, the same comparison as any one of the sides. So let's actually find the perimeter of each triangle. So again, perimeter is just adding up our sides. So if we add up our sides on the top triangle, 8 plus 10 plus 14, we get out our perimeter equals 32. And do the same thing on the bottom triangle. We have 12 plus 15 plus 21. That perimeter comes out to 48. And so let's see if that ratio comes out to be the same. So 32, again, ABC was mentioned first. So I'm going to put that number on the top, 32 compared to 48. Well, both of these I can divide an 8 out of. I can divide 8, let's see, 4 times goes into 32, and then 8 into 48. I believe that's a 6. 48 divided by 8, 6. And that reduces down even further to a 2 over 3, and looky there, we have exactly the same scale factor as we got when we were just comparing sides in that triangle. Alrighty, and then a similarity statement, which a couple of the problems we're doing today are going to ask you to write one out. It's basically just stating what shapes are similar. So our symbol that we're going to use for similar is actually, looks kind of like a tilde, like you would put over an N in Spanish. So a similarity statement is just like a congruent statement where we're stating kind of what pieces of our triangles correspond to the others. So if I had triangle A, B, C, and if I check out my order, kind of going around from the 1 angle to the 2 angle to the 3 angle, I would need to go in the same order in the other triangle, from the 1 to the 2 to the 3. So ABC, triangle ABC is similar to triangle DEF, and we figure out our corresponding parts in a very similar way to when we did congruent triangles. So let's look at some examples. So here we go. First set is, if the triangles are similar with a scale factor of 6 to 5, find the value of x. And so let's see here. They didn't mention what order to look at in the triangle. So when that's the case, take a cue from what the scale factor is compared to what the triangles appear to be. So it looks like that first triangle is larger than the bottom triangle towards the bottom, or towards the base of the diagram with the 28 on it. So I'm going to think that the 6 is going to the top triangle, the 5 goes to the bottom triangle. So I want to write a ratio that is actually setting that equal to the scale factor. And again, if 6 is the larger number, that means our x should probably go with the 6, or in the same place as the 6. The 28 should go in the same place as the 5. And then we can solve this just like we were doing proportions last class. So cross multiply, we're going to get 5x equals whatever 6 times 28 is, which comes out to be 168. And then divide both sides by 5. Again, we are going to get a decimal on this one, but that's okay. That does happen. And I'm getting out exactly 33.6. Okay, so we're going to look at more problems like that actually next week, where we'll be solving for missing sides on our triangles. So keep that in the back of your brain. Okay, number 2, and this is the main thing that we're going to be doing this class, is deciding whether or not our triangles are similar. So if we go back to our definition, for triangles to be similar, they're going to have kind of the same shape, so they're both triangles, and they're going to have the same angles, which if we look at our marks, we have a single arc, we have a double arc, and then we have our triple arc. So I know my angles match, they're marked as congruent, but then the sides are going to be proportional. So the sides are going to have the same ratio. So we need to compare the ratios with all of our sides. Now, it doesn't make sense to match the smallest side on one triangle to the biggest side on the other triangle. So use that as a cue for which pieces to test. So in my bigger triangle, 10 is the smallest number. So I know I'm going to have to match them up with the 4. My medium size on triangle A is 15. My medium size on triangle B is the 6. So those need to get matched up. And then same thing, we've got our 18 is the largest, as well as 7.2 is the largest. So compare those. And so for each one of these, we want to see if this relationship holds true. So I'm just going to throw these all in the calculator and do a division to see what numbers come out. So 10 divided by 4, I'm getting 2.5. 15 divided by 6, again, 2.5. 18 divided by 7.2, oops, 7.2. I get 2.5 out of all of them, so the triangles are similar. Alrighty, but we're not always going to have every single piece of information each time. And we can actually think about, well, what if we just had a smaller amount of items? So think about when we did congruent triangles, we had our rules like SSS and SAS and ASA, and we played around with those triangles and we saw, well, yes, if we have reduced amount of info in these specific orders, we can still prove the triangle's congruent. Well, it's the same thing with similar triangles as well. So there are 3 postulates that we have, 3 main postulates that we could use as kind of a shortcut to prove these triangles similar. So the first one is either AA or AAA, and you can use these interchangeably. But really this comes down to angle similarity. Part of our definition stated that if all of the angles are congruent, that's part of our definition of similar triangles. So wait a second, if all 3 angles in every single triangle always add up to 180, well, do we really need to know all 3 of them? So let's check these out. So example 3, we're given 2 triangles, each one's missing an angle. So we know our triangles are supposed to add up, the angles are supposed to add up to 180. So in my first triangle, if I take 180 and subtract out a 74 and subtract out of 75, I'm left with 31 degrees. And if I did the same thing in the other triangle, well, I have the same numbers that I'm working with. So if I subtracted 75 and 31 from 180, I'd get that same 74 degrees. So even though we were only given 2 angles in the triangle, that's enough to prove, hey, that third angle, whichever one we're looking at, still corresponds to the matching angle in the other triangle. So therefore, these triangles are similar. Alrighty. And so it doesn't really matter if we've got everything labeled with an actual measure or if we just have them marked, given as congruent. So in number 4, we've got another one of those bow tie diagrams. So what can we always mark in terms of angles on those bow ties? We've got our vertical angles that we can mark in the middle. And so with the angles that were already marked, angle V and angle Y, well, we've already got 2 angles that are congruent. So this one also works. So yes, similar. So as long as you have 2 angles that are congruent between 2 triangles, you know the triangles are similar. Again, this won't work for congruency because, again, you could have 2 different sized triangles, just like we did in example 3, exactly the same angle measures, but they are very clearly not the same size. Okay, our next rule that we're going to look at is the Sss Similarity Postulate. So it's kind of like how we broke down our congruent triangles. We're taking each piece of the definition. And so this part of the definition, if all the sides are in proportion, well, then that should be enough to prove that our triangles are similar. And we actually did this in that definition up at the top, although when we were checking those sides, we already had all the angles marked. So looking at number 5, what do you think? Do those triangles appear to be similar? And so think about, well, can I make the same ratios with all the corresponding sides? So let's check it the same way we did before. So again, small side to small side, medium to medium, big to big. And this ratio is a little easier to figure out. We have 3 compared to 6. Well, I know that divides out to 1/2. We have 4 compared to 8. Same thing. Simplifies out to 1/2. And exactly the same thing with 5 compared to 10. 1/2. And so as long as all of your corresponding sides simplify down to that same value, then yes, we're similar. Okay, so let's check that on number 6. And again, these are values I can't immediately see my ratio, so we need to test all 3 of them. So again, small to small. So we need to figure out 30 divided by 24. Medium to medium. So 32 to 25, and I'm always making sure I'm going in the same order, either big to small or small to big, whatever order you pick, be consistent through the whole problem. And we have 35 and 28. So again, you can go ahead and divide these out and just find what value they come out to. I'm getting 1.25 for the first one. So if these are similar, I should get the same exact value for every single other one, and I got 1.28 for the second one. I don't really need to check it at this point, but I do get 1.25 for the bottom one because we got 1.28 for that middle ratio. Unfortunately, these are not similar. So every single thing has to come out to that same ratio, technically the scale factor between the 2 figures. Okay, then our last shortcut rule we have is SAS. So very similar to when we did congruent triangles, we have to have 2 sides in the included angle. But the difference is now, because they're similar triangles, the sides won't be equal, but they should be in proportion. And so in number 7, we have them in exactly the same order. We just have triangle NMP, just looks like a smaller version. I've got my angle in the middle, in between my 2 sides, and so I just need to choose wisely when I write out my fractions and check to see how they divide out. So 8 divided by 6, I'm getting 1.3 repeating. 20 divided by 15, I also get 1.3 repeating. So that means, yes, they're similar. Now, number 8 looks a little trickier because we have 2 triangles hidden in this diagram. So when I see these kinds of problems, I actually like to draw out my separate triangles. I can pretty easily see the smaller one. And then I have my larger triangle, which I'm going to go ahead and redraw. And again, it doesn't have to be perfect. And I'm definitely not an artist, and it's hard to kind of copy over the angles, but it's more about just getting your labels in. So we had this top piece that was labeled as 25 and the bottom piece, which is labeled as 21. Now our 2 triangles were actually overlapping here at that point A. So actually they both have that angle. So there's my angle shared between my 2 triangles. And so now we can check the same thing we did before. So let's see here. We have small side, 15 out on that small triangle is actually the bigger one. So he should match up with the bigger value. 12 should match up with the smaller value. So check your proportions, 15 compared to 25 and 12 compared to 21. So 15 over 25, I'm getting a 0.6. 12 divided by 21, I'm getting a 0.57, and it keeps going. Unfortunately, that's not exact. If I have to round to get there, it's still not equal. So unfortunately, those are not similar. Alrighty, so let's look at a few examples. So we need to decide, are the triangles similar, and if they are, by what rule? So right off the bat, number 9, what kind of information do you have in each triangle? And you can do the same trick that we did before when we were doing congruent triangles, just cover up one of them and look at one triangle at a time. And so it looks like I have my shared angle in the middle and 2 sides. So I'm going to test, hey, will this work with SAS? So again, small side to small side, big side to big side. So 3 over 9, I know that simplifies out to 1/3. 5 over 15, same thing. Okay, so yes, they're similar. I need a similarity statement now. So I need to actually name the triangles. So yes, by SAS. And so just pick a name for your triangles. Again, use your kind of landmarks to help you figure out your order. I'm going to name this small triangle EFG. And notice what I went past. So I went down the small side, hit the angle, went through the big side. So down through the small side, hit the angle, over to the big side. So my similar triangle is going to be triangle RTS. Okay, number 10. So they don't actually give us any sides on this one. So what rule should we try to prove? So we want to try to prove angle, angle, or angle, angle, angle. I know I can mark my vertical angle, so there's my 42 degrees, but my other 2 don't match yet. Again, what do all of the angles in every triangle always add up to? Okay, so let's subtract. So 180 minus 53 minus 42, I'm getting out 85 degrees, which is exactly what we have in the other triangle. So I now have 2 angles that match. And I know without even doing the math, the third angle would have to match up as well because everything adds up to 180. So they're similar, yes, by angle, angle. And then I just need my names. So let's see, let's name this first triangle as triangle ABE, triangle Lincoln. And it went from 53 to 42. Now we don't have a 53 in the other triangle, but we do know that that leftover angle D would have to be 53. And so we went from angle D basically in towards the vertical angle and then around. So triangle DBC. Okay, let's try number 11. So number 11 is another one of these overlapping triangles. So let's draw our 2 separate triangles out. And actually, I'm not even going to bother with the small triangle because he's right there and labeled. But on my larger triangle, again, labeling my sides, I have R, I have Q, I have P. Both of my triangles have P, so I can actually use that angle. And then I need my lengths. So side QK is a 16, but what about the longer sides on the triangle? Yeah, I need to add together my pieces to make this work. So 6 plus 18, that's going to give me a 24. So that's actually my longer side on my big triangle. And then on my bottom side, I have 5 plus 15, aka 20. So that's this triangle. So I could actually prove this in a couple of different ways. However, because I was given all the sides, let's go ahead and check for SSS. Alrighty, so again, small to small, medium to medium, big to big. So let's see here, we have 12 over 16, comes out to 0.75. We have 15 compared to 20, which I believe also comes out to 0.75. And then we also need to check 18 compared to 24. Also 0.75. So they're similar. And technically we could use SSS or we could use side, angle, side. Either one does technically work because they have that shared angle. And then we need our triangle names. So again, we didn't have to twist our triangles around at all. So this one's a little easier. We could use Q, P, Y. And then big triangle, go around in the same order, Q, P, K. All right, number 12. So again, it's another one of these bow tie diagrams. So I can label my angles in the middle. And so now let's look at what info we have. So we do have two sides in both of our triangles. Bigger triangle with 24 and 32, smaller triangle with 20 and 15. Here's the kicker. Where's the angle compared to the two sides? So we have our 24 side, we have a 32 side, and then we have the angle, but it's only touching the 32. We don't have an SSA similarity rule, and it's pretty much the same reason we can't use SSA with congruent triangles. So unfortunately, in number 12, these are not similar. We just don't have the information needed for one of our three main rules. So there's two important notes to make on here. So when we did congruent triangles, we had a longer list. So we actually had, see, just to run through our list for congruence, SSS, SAS, ASA, AAS, and HL. And let's see, for similarity, we have SSS and we have SAS, but we didn't state ASA or AAS. Why do you think that is? Well, one of our rules for similarity is if we have at least two angles congruent, that's enough to prove similarity. So if we have a rule that says two angles works, why would we need ASA? Or why would we need angle, angle, side? It just seems like a little bit of overkill on there. And so no one's ever really bothered to prove those out because we already have the angle, angle rule. So for similarity, we don't actually use those. Now, we do have an HL rule that we could use for similarity. That being said, we're not going to see that very often. So when we actually get to studying right triangles, that might come back into play, but we're really not going to see that for similarity. All right, so big main ideas for this is always check to make sure that your sides are in proportion. And don't forget that all angles in triangle always add up to 180. So if you're ever missing any information for your angles, you can still figure that out as long as you are given two of those measures. As always, let me know if you have any questions. And if not, start working on your practice, and I'll talk to you later.